We're going to do a little quick memorization quiz next Wednesday. I'm going to go ahead and give you guys Monday off next week, so we'll come back on. So we're going to, on Wednesday, we'll do just a quick little memorization quiz. This is going to be, put all phones away, please. Starting up in here, so it needs to be away. It's really simple. This is kind of the Algebra 2 equivalent of memorizing some state capitals. It's no big deal. You don't have to solve anything. All you're going to have to do is just memorize a few things. I'm going to give you a handout tomorrow in class. I won't be here, but Mr. Whitten will give you a, he'll be here. He'll give you a little handout that's got all the stuff you need to have memorized, but I can just kind of tell you what it is. So you're going to need to know all three forms of quadratic functions, right? You need to know if I'm graphing something in standard form and I want to find the coordinates of the vertex, how do I do that? Well, we have the formula h equals negative b over 2a, right? If we are trying to graph a function in factored form and I want to find the coordinates of the vertex, h is the average of the x-intercept, so it's p plus q all divided by 2. And then in any circumstance, if I want to find k, it's always just f of h. So that's really all very simple, right? Very, very simple. You've got to know those things. Okay? All right, so today we're gonna go back to, this is probably like middle school. How many people had my wife in middle school? Anybody? A few people did. All right, good. So probably, maybe you did this with Mrs. Oya, I don't know. This could be. We want to write the number in prime factored form. How did you do that? How did you factor a number like that? With a tree, exactly, with a tree. So we've got 2520. We're going to make a factor tree. Remember the rules for a factor tree. Every time you branch a factor tree, you're going to form two numbers that multiply to the number above, so are factors of the number above. What are two factors of 2520? And I'll give you a hint. That's a 0. 10. Okay, so we could do 10 and 252, right? And then 10 is going to break up into what? 2 and 5. Okay, good. So we're going to get 2 and 5. And 252 is going to break up into what? A bunch of different choices. Doesn't matter. But the fact that that's an even number gives you a hint on one of them. 2 and... Well, you tell me what's going to be 2, and then half of 252 would be 126. There you go. Okay, that's even. So I could get a 2 again, and then that's going to be, what, 63? Which breaks up into what? 2? I could do that. I could do some bigger ones. I could do 3. I could do 7 and 9, couldn't I? 7 and 3 would have worked too. 7 and 9, and then 9 breaks up into 3 and 3. And so you always stop. Like I made the numbers that we stopped on blue, but what's true about all the blue numbers?
They're prime numbers.
They're prime. Yeah, so when you get to a prime, you stop. And so the answer is 2520 is equal to 2 times 5 times 2 times 2 times 7 times 3 times 3. Can we write it in a little shorter way? Okay, 2 cubed, right? So that takes care of all the 2's times 3 squared, and we'll gradually work up from smaller to bigger prime factors. So we get 3 squared, takes care of those 2, times 5 times 7. There we go, right? Got it. Okay? That's prime factorization. So why do we go through that? Well, 2 reasons. One of them is because I want to point out that this is the number equivalent of what we've been doing in class, right? When we factor a quadratic function, or later on they'll be bigger than quadratics, polynomials that are bigger than quadratics, our goal is to break it down into the smallest possible pieces. Well, we just did that with a number. This is the smallest, these are the smallest possible pieces of that number, okay? All right, so here's the other reason we do that. Because it's very useful to us when we want to simplify radicals. Okay, and you would have done this in Algebra 1. I'm not sure, you probably wouldn't have done any of this in middle school. This would have been like an Algebra 1 thing. So here's how we can use that. Now, this looks pretty complicated, but if we take advantage of a factor tree, we can make this really simple. So let's take everything inside the square root is what we're trying to simplify, right? Our goal here when we're simplifying a radical is to get as much out in front of the radical as possible. We want to leave as little stuck inside the radical as possible. So whatever number is inside the radical, that's what we call the radicand, we're going to factor that using a factor tree. Well, that's a 0, so what can we do? Divided by 10. So we're going to get 10 times 441. Good. Okay. 10 breaks up into 2 and 5. Now what about 441? What's a number that goes into 441? 2 doesn't go into it because it's odd. 1 does, but 1 doesn't help us. 3 does. How'd you know that? You're right. There is a way you can tell that 3 goes into that.
It's odd prime number.
No, that 3 doesn't go into every odd number. If you add the digits up, 4 plus 4 plus 1 adds up to 9, doesn't it? 9 is divisible by 3. When you add the digits of a number, if the result is divisible by 3, then the original number is divisible by 3. So if I divide 3 into this, now 5th period, people have never seen this kind of division. So if I'm dividing 3 into 441, see if this makes sense. 3 goes into 4, how many times? Goes in 1 time with 1 left over. Or sorry, with 1 left over. So now I'm going to ask the question, 3 goes into 14, how many times? 4, with how many left over? 2. And now I'm going to ask the question, 3 goes into 21, 7 times, right? See how we can do that? Kind of a good little trick for just dividing on the fly. Okay? Okay, so now what's a number that goes into evenly into 147?
7.
4. Well, I mean, those might. 4 doesn't for sure because it's odd.
3.
3 does. How'd you get it?
4 plus 1 plus 7.
It's 12, yeah. And 12 is divisible by 3. So once again, we know 3 goes into it. Let's try this trick again. Does 3 go into 1? No, so we got to scoot over 1, 1 digit. 3 goes into 14 how many times?
4.
Into 14, 4 times, yeah.
14. I thought you were going to say 4.
4 times with 2 left over, right? So now 3 goes into 27, 9 times. There you go. Okay, and then 49 breaks up into 7 and 7. Okay. Now, why do we do this? So let's write this out as in its simplest form. So we're going to get 2 times 3 squared, right? Times 5 times 7 squared. Everybody agree? Okay. So then the square root of 4410 we could write as the square root of 2 times 3 squared times 5 times 7 squared. We're going to come up with a shortcut so we don't have to do this work every time. But the first time through we're going to. Okay, here's a property. See if this makes sense. All right, does this make sense to you? That if I did the square root of a product of numbers, A and B are just numbers, so the square root of A times B, does it make sense that I could write that as the separate square roots, the square root of A times the square root of B? I'll prove it. It works. Like what if we did the square root of 4 times 9? What's 4 times 9? 36. So that's just going to be 6. Or that's going to be 36, right? The square root of 36 would be just plain old 6. Well, if I broke that into the square root of 4 times the square root of 9, what's that going to be? 2 times 3. Yeah, it works, doesn't it? Okay. It doesn't just work in that case. It works in every case. That's a property of radicals. So I'm going to use that to rewrite this as a product of 4 different radicals. I'm going to split it up. Each one of those factors, I'm going to give it its own radical. So it's going to look like the square root of 2 times the square root of 3 squared times the square root of 5 times the square root of 7 squared. Now, why is that useful? Why is that so useful? What's going on? What happens if I square root something that's squared? Cancels it out, right? Because square roots and squares undo each other. So look, those cancel and I just get a 3. Those cancel and I just get a 7, right? So then this whole thing is just equal to 3 times 7 times the square root of 2 times 5. Agreed? Everybody see that?
We're just trying to break it down as quick as possible.
Yeah, as much as possible. And so then our final answer would just look like 21 outside times the square root of 10 inside. Okay, that's a lot of work to show. I would claim that we could do that in one step. Here's how we can do it. When you take the number that's inside the radical and you factor it, all you have to remember is this one simple rule. Couples go out, singles stay in. Couples go out, singles stay in. So we're going to look at all of the prime factors that we got, and let's circle numbers that are in a couple, and let's put a square around numbers that are single. Okay? So what do we find here? Well, what are my couples?
3 and 7.
Okay, good. So we got a couple of 3s, and we got a couple of 7s, and I got single
2 and 5.
2 and single 5. So that tells me that whenever I'm simplifying a radical, I always know that I'm going to get an outside answer times an inside answer. Couples go out and singles stay in. So any number that's a part of a couple gets to go outside. So look, I have a couple of 3s, and so I write a 3 outside. I have a couple of 7s, so I write a 7 outside. I have a single 2 and a single 5, and so 3 and 7 are my outside numbers, 2 and 5 are my inside numbers, and what do you know? If I simplify that in one step, I got that answer. Pretty good, huh? Okay? So here, let's practice one of those first. Before we go any further, get out your notebooks and just try one of these. Try one of these on your own. A lot of times it takes a couple examples to get the hang of it. So we're going to take the number inside the radical, right? We'll do a little side work here. The number inside the radical, 594. So I got to make a factor tree. So what's something that goes into 594? 2. And then 2 goes into 5 2 times with 1 left over. 2 goes into 19. 9 times with 1 left over. 2 goes into 14. 7 times. There you go. Okay? Now what? 3. Yeah, good. We can do 3, can't we? So 3. 3 doesn't go into 2, but 3 goes into 29. 9 times with 2, with 2 left over. 3 goes into 27. 9 times. Okay? And then we could do 3, but we could even do probably an easier one. 9 and 11. Right? And 9 breaks up into 3 and 3. So now let's count our couples and singles. Okay, you see any couples? 3 and 3, so I get a couple of 3s and no other couples, right? So all the other things are going to be singles. Okay, so then we get outside number and inside number. What's my outside number? 3. Right, and that comes from right there. What's my inside number? 2 times 3 times 11. And so if I simplify this whole thing, I get 3 times, well, 2 times 3 is 6. What's 6 times 11? 66. So we're going to get 3 times the square root of 66. Okay? Okay. All right, so why do we do this? Oh, actually, one more. We got to do a couple more. We're not quite there yet. So what about this one? What are my options here? I want you to think about this. Let's try to be very logical about this and strategic. So I'm doing the square root of 2 times the square root of 10 times the square root of 15. So one thing I could do is what? Combine them. Yeah, I could make that one big square root, couldn't I? So I could turn that into, if I wanted to, I could turn that into the square root of 10 times 15 would be 150 times 2 is 300. And then break down 300, right? I could make a factor tree out of 300. Agreed? Okay, but we could be a little smarter about it than that. We could do this. We could say, okay, well, let's make a factor tree out of this product, right? If I've got 2 times 10 times 15, instead of writing it as 300, just write it that way. Write it as 2 times 10 times 15 and factor each of those separately. Well, 2's already done, isn't it? Okay, what does 10 break up into? 2 and 5, and 15 breaks up into 5 and 3, right? Easier. It's already part of the process has been done for me because 300 really would have broken down into a product of those three, wouldn't it? Everybody agree? Okay. So now we can do couples and single count. See, do you see any couples?
5 and 13, 5,
2 and 5, single 3. And so my answer is going to look like, what's outside? Good. 2 times 5, and what's inside is 3. And so we just get 10 radical 3. Okay, make sense? You remember doing maybe stuff like this. Okay, what about this one? What do we do when we divide square roots? Okay, now what you're thinking of, I think, what you're probably thinking of is what happens if you divide like bases. Like if I have x to the 5th divided by x squared, then I get x to the 5 minus 2 equals x cubed. That's a little different. So if I'm taking a square root of a fraction, I can just square root the top and the bottom separately, right? What's the square root of 36? 6. What's the square root of 16?
4.
And what is 6/4 reduced to? Done. Easy, right? Not all that easy, though. Sometimes we get problems like this. Okay. And, okay, the top is a perfect square, right? The top is going to give us, top is going to give us 13. But what about the bottom? Bottom's not a perfect square, is it? Okay, so we got to do some side work here. What does 50 break up into? 5 and 10. 10 breaks up into 5 and 2, doesn't it? Right? Okay, and so look, we get a couple of 5s and a single 2, right? So on the bottom, we're going to get a 5 outside, and I'm going to get a 2 inside. Okay, do you remember, though, in Algebra 1, is that an okay answer? What's the problem with that answer? Something's wrong with that.
It's not simplified.
It's not simplified. How come?
Because we still have that square root.
Yeah, you can't have a square root on the denominator. We have to rationalize the denominator. Did your teacher ever teach you no tenths in the basement? You ever learn that? You ever learn that way? Okay. So no tenths in the basement, no radicals in the denominator. So we got to get rid of the radical in the denominator. Now think what our options are. Now I want you to really think about this concept for a second. If I were to put these two numbers into a calculator just like that, I'm going to get some decimal answer, right? When I'm all done with this problem and I've written it in simplified form, what if I put my answer into a calculator? Should I get the same decimal or a different decimal? Same, right? It's got to be the same. I'm not changing the value of the number, I'm just changing the way it's written, correct? So what are the things that I can do to a number and not change its value? What could I add? You know what we're going to do.
0.
So I could add 0 and I wouldn't change it. What could I multiply by and not change a number? 1. Okay, so we're going to multiply by 1 in this case, but we're going to multiply by 1 in a special form. We're going to multiply by 1 in the form what divided by what?
5
Okay, and I don't need the 5. All I really need is just the square root of 2 in both the top and the bottom. If I divide something by itself, isn't that equal to 1? So I've just multiplied my number times 1. I haven't changed the value, have I? Why did I do that, though? What is the square root of 2 times the square root of 2? Ah, that's the square root of 2 squared, isn't it? That's the same thing as saying the square root of 2 squared, and the squared cancels the square root. Or I could think of it as the square root of 4. Either way, I get 2 out of it, don't I? Right? And so now what happens? So now I end up getting, on the bottom, I've got 5 times 2, which is 10. And on the top, I've got 13 times the square root of 2. Problem solved. Right? Now the radical is on top where it's supposed to be and not on the bottom. So what's my strategy? It's very simple. After we simplify both the top and the bottom of the fraction, if I have a stranded radical on the bottom, right, I'm just going to multiply the top and the bottom by the stranded radical, the stranded square root, okay, to get rid of the radical. Okay, let's try another one. So you guys try this one. Try to simplify this. First of all, I might want to see, could I reduce that fraction and make things simpler? Does 8 over 27 reduce? No, it doesn't. Okay. So try that. It's the first step. Simple.
Put in the radical.
Okay, but first step is, I'm just going to split it up into separate square root on the top and square root on the bottom, right? Okay, what am I trying to do next? Simplify. Make them as small as possible, right? I want to get as little under the radical as possible. So what about the top? I got to make factor trees for these. What about my 8? What's that break into? 2 and 4, and 4 breaks into 2 and 2. So I got a couple of 2's and a single 2, right? So on the top, I'm going to get 2 outside, 2 inside. Now, what about the 27? The 9 is, so I get a couple of 3's and a single 3. Right? Okay, so let's put that down here. Now what? What's the problem here? Okay, good. The problem with this is the square root of 3 on the bottom. The square root of 2 on the top is fine, isn't it? It's the square root of 3 on the bottom that's an issue. So I'm going to multiply the whole thing by square root of 3 over square root of 3. And what's that going to give me on the bottom? No. I'm going to get the square root of 9, which is 3. So I'm going to get, oh, you're right, it is 9. What am I saying? 3 times 3, whoops. 3 times 3 is 9. And on the top, I'm going to get 2 times, what's the square root of 2 times the square root of 3? Square root of 6. There you go. That's my answer. Okay? All right. So last issue. Now, why are we doing this? Here's the why. The reason we're doing this is because this gives us a really, really simple way to solve some quadratic equations. So when we're solving a quadratic equation where we can point to a single variable like we can here, then that means that we can just isolate the variable by reversing the order of operations, just like we did at the start of the year with linear equations. Do you remember solving equations like this? Like I might have given you one where it said something like 2x minus 3 equals, let's say 18, or no, 17. What would you do to solve for x? You'd add 3 and divide by 2, wouldn't you? You just reverse order of operations and isolate the x. Remember talking about all that stuff? Well, looky here. We can do the same thing, can't we? I can point to a single x there, right? So if I reverse order of operations, I ought to be able to isolate that x. So what are the steps going to be? We want to reverse PEMDAS. So we go in that direction to solve or isolate, right? We're trying to isolate an x. So what's the first thing we're going to do? Is there any addition or subtraction I need to undo?
Subtract 44.
Subtract 44. Okay, so step number 1 is going to be subtract 44 from both sides. And that's going to give me 4x squared equals 398. Good. Okay, what's next? And work my way up. What's next?
Divide by 4.
Divide by 4. Right? I have to undo some multiplication by dividing. I'll divide each side by 4, and that's going to give me x squared equals, let's do our trick. 3 goes into 39 how many times? Oh, 92. You're right. So 4 goes into 39 how many times?
9?
With how many left over?
6? No, 3.
3, okay. And then 4 goes into 32?
8.
8 times. Okay. So good, we're getting there, right? So we move our way up the ladder here. What's the next thing I've got to do? Well, it's exponent row. Are there any exponents I need to undo? Yeah. Yeah. So now okay, so how do I undo something squared? Square root both sides. Okay, this is the part you got to remember though. If I'm going to square root both sides, what do I get on the left side? I get x, right? The square root of x squared is x. I got to simplify the square root of 98. Let's make a factor tree. What's that?
2.
What's 49? Okay, so I'm going to get a couple of 7s, single 2, right? So I know I'm going to get a 7 radical 2. Is that my answer? Say it again. Well, I could check it, but I mean that's my solution, but I'm missing something important.
Other x.
Say it again.
The other x.
What's the other x?
6.
You don't remember this? What happens if I square root both sides of an equation? What do I always have to include when I square root both sides? I gotta put a plus or minus there. Remember that? Okay, that's a rule. I'm gonna write this down. If you solve an equation by square rooting both sides, you must include plus or minus in your answer every time. Okay, here's why. Nobody ever shows the reason why. They just tell you to remember that. I'm going to show you why this works, why this is the way it is. Okay, what is the square root of x squared?
X.
It's not x.
Negative.
It's not x. Let's examine it for a second. It sure seems like it ought to be x, but it's not. Let's turn it into a function. So f of x equals the square root of x squared. Let's try a couple things. Let's evaluate our function at 2. So what is the square root of 2 squared? 2 squared is what? 4, and what's the square root of 4? 2. So f of 2 is 2. If I input a 2, I output a 2. I'll tell you what, let's do, yeah, we'll do that, okay. You know what, I'll tell you what, we'll do that, that's fine. What if I input a negative 2? This will work. What if I input a negative 2? What's the square root of negative 2 squared? What's negative 2 squared? 4. What's the square root of 4?
2.
Oh. Well, hold it now. What function do we know that does that? If I input a positive number, I just get the same number back. But if I input a negative number, I get the positive number out. We know a function. We've worked with one that does that job.
Inverse?
What is it?
Inverse separation?
No. We've learned, you've known about this one for a long time, but we've used it earlier in the year. What kind of a function do we have where if I input negative 13, the output is positive 13 guaranteed? Absolute value. That's it. Absolute value. So really, the square root of x squared is actually equal to the absolute value of x. It's not equal to x. And so the missing step here is we get the absolute value of x equals 7 radical 2. But think back to our unit that we did on solving absolute value equations. If the absolute value of x is equal to a number, what did that mean? Either x equals this or x equals that. What were the two things it could equal? Well, I mean, like if we had, I mean, we did a bunch of stuff like this, right? Like if we did much harder problems than this. You'll remember this. We did things like you guys did really hard problems. You did things like the absolute, this isn't even that hard. Like if you did the absolute value, or 2 times the absolute value of x plus 1 equals 10. What'd you do to solve that? What'd you do first?
Isolate that.
You isolate the absolute value, right? So we divide each side by 2, and we get the isolated absolute value equals 5, right? And then didn't we say whatever's inside the isolated absolute value, we're going to trade the one absolute value equation for 2 regular equations. So whatever's inside either equals 5 or negative 5, right? Remember doing this? Whatever's inside equals negative 5. And then we would just solve those. I'd get 4 or negative 6 would be my solutions, right? Well, this one's much easier. The case we're working on right now, if the absolute value of x equals 7 radical 2, then doesn't that mean either x equals positive 7 radical 2 or x equals negative 7 radical 2? There's my plus or minus. Okay, do you have to show that work every time? No, don't. Just do this. Just skip from here down to here. But you remember, if I square root both sides, I have to include a plus or minus. Just remember that step. No, on Moodle, you have to enter them separately. Yeah. Okay? But we got our answers. So you see why this is useful then. Why do we need to know how to do the simplifying radicals? Well, because when we isolate x, sometimes we've got to simplify square roots, don't we? Right? And we're going to have to do it again and again for the next, over the next week or so, we'll be doing a lot of it. Okay? All right. That's probably a pretty good place to stop.
Like 4